Suppose you've prepared a buffer, and in making that buffer you used an acid with a pKa of 5.00. Now, we can anticipate that around pH of 5, we're probably going to have a pretty decent buffer. And remember, the reason for that is that when we do our Henderson-Hasselbalch equation, we say that pH equals pKa plus log of our of our base form over our acid form. And so if we have a 50-50 mix, which is what happens at the pKa, then we're going to have this be the number 1 overall. The same number divided by that number. Log of 1 equals 0. So it'll be at pH equals pKa. Now let's go ahead and see exactly what that tells us, though, about how good our buffer is going to be in different areas. Now, we can use the buffer equation over a pretty wide range if we're being very careful, but we shouldn't. And I'll show you why right now. If we're concerned about when it's actually a good buffer, we can calculate something called buffer capacity, which we do as beta, or you can think of that as an italic B, either way, but really it's a beta. In beta, we're talking about the change in the concentration of our base that we're adding, and seeing how much it's going to change its pH when we do so. In other words, this will be the moles of our base or acid that we're adding. So as we change how much we've added, how much does pH change too? If things are buffering very well, we can add a lot of acid or base and see a small change in pH. So that's what buffering capacity is going to tell us. When buffering capacity is a high number, that's going to be because small changes from big changes. In other words, big beta means it's resisting. There we are. Okay, now let's go a little bit deeper on that. So, how much base or acid are we having to add to create a pH change? Now, if we were to plot that, and I want to have this be a very careful cautionary statement. Do not think this is a titration curve for even 1 second. This is a common error that I see people make. Let me point out what we're doing. On a normal titration curve, this would be our x-axis, how much we've added, and then our normal y-axis would be pH. So we've actually kind of rotated it 90 degrees. Make sure that you're not thinking that they're the same. But this is the way that they actually do conceptually make sense when we compare one against the other. So be careful. Now, if I'm at a low pH, acidic pH in other words, I probably haven't added much of my base yet. I probably just have my pKa of 5 acid sitting there. So I just made a solution with just my raw acid, HA. Now I'm going to start adding in some base. And as I add some base, I'm going to be reacting away one of those protons to form water with my base. OH minus plus H plus gives me water. Now I've got an increasing amount of my A minus. You can see how that as we keep on removing this with OH minus, we're going to be pulling things forward through Henderson-Hasselbalch. Now, that makes some sense to us, I hope. Now, as we start adding in some of that acid, it's going to react. It's going to start pulling things to the point where we're actually seeing our pH start to change. Small additions of base are going to do a lot of change at first. And that's going to start creating some of our conjugate base. Once we've done that, we have acid, we have conjugate base. We say, aha, Henderson-Hasselbalch does apply. Now, if we were to actually plug it through the calculations, for each of these spots we'd be able to calculate exactly what our concentration is. Now, you'll notice that right around here, where pH equals pKa, pH of 5, we're going to be to the point where we're halfway through the amount that we need to get to our equivalence point. In this case, they actually were setting it up so that the amount of acid present was going to be 0.10 molar solution. and we're using equal volumes once we get to that point. All right, so that would be the end point if our titration curve was a titration curve. It isn't, so be very careful. End of titration. All right. Now you can see that halfway to that point, we have that 50-50 mix. At that moment, we're going to have the best buffer possible. Now think through what that really means. It means that right now, we have 50-50 of our acid and base forms. If we add a little bit more acid or base, we're going to just barely unbalance this fraction. The number is going to stay very close to the number 1. We plug the very close to the number 1 value into the log in our Henderson-Hasselbalch equation, and the log of something very close to 1 is still going to be very close to 0. So, plus, I'm just going to put something very close to 0. That's going to be right here. Now as we get further and further from that spot, we're going to have a bigger and bigger imbalance. We'll still have the ability to buffer. We just can't handle as big of a change in our concentration of the acid or base that we add without causing a bigger change in the pH. That doesn't mean it's not buffered, it just means it's turning into a wimpy buffer. And eventually it's going to turn into a very wimpy buffer. Now notice that when you go plus or minus 1 pH unit around pKa, things are still going to be a pretty decent buffer. As you get further out from there, they become less and less good of a buffer, but it's still going to have some buffering capacity. So the rule of thumb that we use is that buffers work over a 2 pH range. And that's around pKa. You'll still have a little bit of capacity outside of that range, but it starts getting wimpy enough that we don't really want to use it to start controlling our pH very much. So this is what we use to calculate our buffer capacity, and this is what all of it means. But don't let yourself fall in the sucker trap later of telling me this is halfway to the equivalence point. Because it's not. When you're looking at a real titration curve, that will be the end point. That's not the spot with good buffering. So don't try to make a connection for this being a titration curve, or you will be bit in creative and innovative ways.